Alright, what's going on, guys? Welcome back to the channel. ErickMed here, and today we're going to be doing a chemical and physical foundations of biological systems breakdown. We're going to be breaking down this passage and answering the questions. I'm going to show you guys how I break it down, my thoughts going into it, and all that stuff. So this passage is from the AAMC section bank, okay? So when you go on the AAMC website, and you buy all those practice materials for the MCAT, they give you all this stuff. They give you like a question pack, sample test, a section bank, a guide, all that stuff. So the section bank, that is what's known to be hard. Like the section bank passages are hard. Like people in the Reddit for the MCAT, my friends, when I did it, like the section bank is hard. Like those passages are pretty difficult. Some are like more difficult than the actual test, and like I can account for that. Like some of these section bank passages, they were harder than the passages during my actual MCAT test. So that was only some of them. Like some of the passages on my MCAT test, they were like of section bank difficulty, but some other passages were not like this hard. I got a 130 on this section last time I took the MCAT. I could have got a 131 or 132 if I had remembered my kinematics equation, but I didn't. That's so low yield. Like I thought it wouldn't pop up, and it did. And I got those questions wrong. I already know what questions I got wrong. So that goes to show you, like literally anything could just like pop up on the MCAT. But anyways, enough talking, guys. Go ahead and read through this passage. I'm going to scroll down here. Pause it whenever you need to. So go ahead, read through this passage. This is question number 1. This is question number 2, number 3, number 4, 5, and I think there's one more, and that's it. That's 6. Okay, yeah, there's only 6 questions here. So pause it whenever you need to, guys. Write down your answers, and hopefully get everything right. And if not, then I'll show you where you fucked up. All right, let's begin. Passage 7. Okay, so my mentality going through this, and like the best way to answer, these section bank passages on the MCAT, Chem Phys, and stuff like that, is this passage, the passage they give you, it can be a little complicated. It can be a little like what, like that's like the, I guess, hard part for answering MCAT questions. But the questions here, like the questions that they give you, that they want you to answer, that's not that bad. These questions are easy. All this stuff here, that can be a little complicated. But if you break it down correctly, and you know what the heck they're testing for, what the experiment is about, then everything should be easy, piece of cake, and you should get all these questions right. All right, I haven't looked at this before, so let's jump right into it. Okay, let's see. 2 students performed an assay to determine the concentration of lactase in a commercial preparation used to make milk consumable by those who are lactose intolerant. Okay, right here, right away. Performed an assay to determine the concentration of lactase. I'm going to highlight this. This is what they're going for in this experiment. They already told me straight up, so I'm going to highlight that. They want to know the concentration of lactase. So let's see how they do it. How do they run this experiment? Lactase catalyzes the cleavage of lactose, beta-D-galactopyranozole 1,4-D-glucose into beta-D-galactose and D-glucose. Oh, okay. Yeah, what? Oh, that's why. This arrow here, I guess it means that they're connected. And then after lactase, we get 2 separate molecules, beta-D-galactose and D-glucose. Okay, yeah, so this was lactose. There's one big thing here. And then using lactase, we broke it up into beta-D-galactose and D-glucose. Yeah, I was a little confusing with this arrow. Like, what the heck is that arrow? But a glutamate residue in the active site donates a proton to an oxygen atom. Another glutamate on the opposite axial side acts as a nucleophile to liberate D-glucose and generate an alpha-D-galactopyranozole modified enzyme intermediate. Okay, we got some organic chem here. Then Glut1 deprotonates water, and the resulting hydroxide ion acts as a nucleophile to liberate beta-D-galactose and regenerate the enzyme. Okay, they're telling us a mechanism here. How the heck does lactase break down lactose into beta-D-galactose and D-glucose? The way this enzyme, this glutamate 1 is on the enzyme. Okay, glutamate 1 and glutamate 2 are on the enzyme. And the way that we liberate beta-D-galactose is we deprotonate the water. And because we deprotonated water, it's now OH, it's a hydroxide. Great nucleophile. I'm sure it did nucleophilic attack, and the leaving group was beta-D-galactose. Okay. All right, I'm going to highlight this. Okay, that makes complete sense. That's a classic SN2 reaction, something that you really need to know. So yeah, it makes sense. Rather than use lactose as a substrate, which is difficult to quantify spectroscopically, the students chose compound 1, which produces beta-D-galactose, and yellow compound 2 under the action of lactase. All right, that makes sense. Okay, so instead of using lactose, they were like, okay, let's use something else that has a yellow compound, and this yellow compound we can quantify spectroscopically. Okay, that's how basically you got to know spectroscopy for the whole MCAT. Like spectroscopy, they could test it in the Chem Phys section, the BB section. Like they'll test that everywhere. So that's something you guys have to know. Basically spectroscopy is like you use light to determine the concentration of your substrate in a solution. Okay, and they're using yellow here. So I'm sure they're going to ask a question about this. Okay. The students prepared stock solutions of compound 1 in 4 different concentrations in a pH 7 buffer. Okay. Compound 1. A stock solution of the enzyme was prepared by diluting 100 milliliters of the commercial preparation to 25 milliliters in the buffer solution. Okay, we have a dilution here. We went from 0.100 to 25 milliliters. Okay, so we diluted 0.100 milliliters to 25 milliliters. Okay. Experiments were initiated by mixing 1 milliliter of each substrate solution with 1 milliliter of the enzyme solution. Okay, so they did 2 things to prepare the enzyme solution. They first diluted it to 25 milliliters, and then they mixed it with something else. So we have 2 things going on here. Okay. Oh, I just look at this. We have a line work beaver plot. Whenever you guys see line work beaver plots or Michaelis Menten, whatever, all that stuff, that you get happy for that. Okay, that's fun because those stuff are easy. That's so easy. You have to master those 2, the line work beaver plot and the Michaelis Menten, because odds are they're going to ask you something about this and like what happens to inhibitors here or something like that. But it's easy. It's literally 3 points. So be happy when you see those. The initial rates of VO were measured for each trial. The students then plotted 1 over VO, which is initial velocity right here, versus 1 over S. Makes sense. That's how we learned it in biochem class, to determine Km, Vmax, and enzyme total for the 4 trials. Cool. I'm not going to look at this now. I don't want to waste time. All right. So what the heck is this passage doing? Well, they're like, okay, these people want to know about lactase, how it works. Okay, it told us how it works. And they told us, they want to quantify it spectroscopically. They want to say, okay, how much lactose do we have here? How much substrate did this lactase break down? Lactase was in here. It broke it down. It broke lactose down. And by measuring the product concentration through spectroscopically, we're able to determine the concentration of our product using the light. Okay. And then they just gave us some, all right, so this is easy passage, Let's see. Which experimental technique was most likely used by the students to determine the rate of reaction? The rate of reaction. Okay, they mentioned, okay, we can determine the rate of reaction by determining the product, the amount of product we have. How can we determine the amount of product we have? Well, we can determine the amount of product because it's yellow, okay? Compound 1 makes something yellow. We have a yellow, and they quantified it spectroscopically. So let's see. Monitor the increase in absorbance of the solutions at 200 nanometers. Monitor the increase in absorbance of solutions at 360 nanometers. Monitor the decrease in absorbance of solutions at 200 nanometers. Okay, so they use this yellow compound. Okay, and what they do, this is something you have to know. Like, this is some content review you guys have to know. In spectroscopy, if we have a yellow compound here, the more yellow our solution is, the more product we have in that solution. The less amount of yellow we have, like if we have a little tint of yellow, then that means we have very little product in our solution. If we have a very, bright yellow, neon yellow in our color in our solution, that means we have a lot of product in there. So what they do is they measure the increase in absorbance. Okay, the more absorbance we have, the more yellow, the more product we have, and that can determine the rate of the reaction. So we're not going to be measuring the decrease. That makes no sense. Why would we measure the decrease in absorbance? That's just going to make finding our results so much harder. It's more about the increase. More absorbance, more product. More product, most likely the rate of the reaction was, faster. Monitor the increase in absorbance of the solutions at 200 nanometers. Monitor the increase in absorbance of solutions at 360 nanometers. Okay, I don't know yellow. I don't know what the wavelength of yellow is, but 200 versus 360. The visible light spectrum, I know that it's from 350 to 780, around there. That's the range of the visible light spectrum. I don't think this visible light spectrum is from 200 nanometers. That seems very low. That's a very short wavelength. I think the visible light spectrum is starts at 350 or 360 or something like that. So 200 is out. That's out of the visible light spectrum. Why would we want to? No, this makes no sense. It's yellow. If we can't, why would we measure something we can't even see or absorb? We have no idea. So I think we would monitor the increase in absorbance of the solutions at 360 nanometers. That makes the most sense. We want to see the increase in absorbance, at 360. Yeah, that makes complete sense. Let's see. Boom! All right, let's go. And that's the explanation, guys, if you want to read a little further. That was a hard question. That required you to know your fucking spectroscopy like the back of your hand. Yeah, this question, if you got this wrong, then it's probably because you don't really know research techniques and stuff like that. So definitely look into that. Okay, next question. Based on the description provided, if lactose was hydrolyzed under the action of lactase in O18 labeled water, in which location would the label appear? Okay, they told us here what happened. Let's see. So glutamate 1 deprotonates the water, and the resulting hydroxide ion acts as a nucleophile to liberate beta-D-galactose and regenerate the enzyme. So this is a classic SN2. Okay, we have water, H2O, deprotonate it, we get an OH, we get an hydroxide ion. This hydroxide ion goes as a nucleophile and hits something. And then when it hits something, when it attacks something, we get beta-D-galactose as a leaving group. So this OH, if we labeled it, it's going to go and attack. It's going to go and attack something and liberate beta-D-galactose. So neither the galactose nor the glucose products, no. It's going to be on something. The glucose product only. No, this is talking about beta-D-galactose. Glucose was liberated from the GLU2, from the glutamate 2. We're talking about the one that gets deprotonated the water. We're talking about the water. So no, it's not glucose. Galactose product only. Yeah, that makes sense. That makes sense. This hit a carbonyl or some shit. The OH came in and attacked, and it stuck with the beta-D-galactose. That makes a lot of sense. Both the galactose and glucose products. No, it's not on the glucose. It's not on the glucose. It's not. The glucose was liberated from some other shit. We don't know what it was. The glutamate was a nucleophile for the glucose, not the water. Water released beta-D-galactose. Glutamate released D-glucose. So the galactose product only. Boom! All right, let's go. And this is the explanation, guys, if you want to read it. For what mechanistic reason does G1 of lactase first act as a Bronsted acid during catalysis? Bronsted acid donates a proton. G1. G1? What do you mean G1? Do they mean glutamate 1? Because that's what's happening here. I hope they mean glutamate 1. Why would they say G1? That's bad wording. Yeah, that's such bad wording. Bad wording, MCAT. You guys need to change that shit. Okay, so a glutamate residue in the active site donates a proton to an oxygen atom. What the heck is this oxygen atom? And then another glutamate on the opposite axial side acts as a nucleophile to liberate D-glucose and generate an alpha D, the intermediate. Okay. All right. Okay, I understand what's happening here. So this oxygen atom, this is on the sugar. This is on the lactose. And the glutamate residue has an OH or has an H somewhere. And then this oxygen atom took that H. Why would the glucose oxygen atom take a proton? Well, it's not to become an OH and hit something and acts as a nucleophile. No, we have another glutamate that acts as a nucleophile, and we have the water that acts as a nucleophile. The only reason why that oxygen atom would take on a proton is because it's probably a leaving group. And this oxygen atom belongs to the lactose. This oxygen atom belongs specifically to the D-glucose on lactose. Okay, D-glucose took that hydrogen atom to become a better leaving group so it can get kicked out from the nucleophile glutamate. And it says it right here. Glutamate acts as a nucleophile to liberate D-glucose. Okay, that makes sense. And that happens after, First, this is a lot of organic chemistry stuff here. First, we get protonation of our oxygen atom. That becomes a good leaving group. And then we have the nucleophile attack to free that leaving group. We don't have, nucleophile trying to attack first and then protonation of the leaving group. Like, no, that's backwards. First, we get a better leaving group, and then nucleophile comes and liberates that. So I don't have to, this is 100% this one. I don't have to look at it. Boom! Next question. What is the Km of compound 1 with respect to lactase? Boom! I told you guys, these are your favorite. When you see this, get happy because these questions are so easy. And this is section bank stuff here. This is supposed to be hard. It's not that bad. Look at this. What is a Km of compound 1 with respect to lactase? Okay, if you can't answer this, you got this wrong, then go and review enzyme kinetics because that is so high yield and it's so easy. It's free points, literally free points. So what is the Km? If you don't know already, it's -1 over Km is here, and then 1 over Vmax is here. So the x-intercept is -1 over Km. What is the Km? Well, we have -0.05. So 1 over 0.05 is what? 20 milli. Yeah, it's this one. Yeah, you just have to know your enzyme kinetics equations for that. Easy points. Boom, next question. What method did the students use to calculate Vmax? Experiments were initiated by mixing 1 liters of initial rates. Okay. Vmax was calculated as Km times Kcat. No, that's not Vmax. Vmax is not that. Vmax is like Kcat times, I believe, enzyme total concentration. Not that. Km, it's not that. Vmax was determined as the fastest initial rate of compound 2 formation obtained during the kinetics experiment from the passage. Initial rate? I don't know what they're saying there. Hold on. Vmax was calculated as S times Kcat for the trial with the highest substrate concentration. No, that's not Vmax. Vmax was determined as the inverse of the y-intercept of the graph shown in figure 1. Yes, the y-intercept is 1 over Vmax. Okay, that's the y-intercept for a line work beaver plot. And for this question, to answer it, they're testing your understanding of Michaelis-Menten and line work beaver plot. Like why we go from a Michaelis-Menten to a line work beaver plot. Why do we take the reciprocal of Vmax? Why do we take the reciprocal of Km? And the reason why we do that, a quick little lesson here. The reason why we do that is because you can't, in a Michaelis-Menten, you can't really know the exact Vmax. It's an asymptote. The line approaches as an asymptote. It gets closer and closer and closer to Vmax, but you don't really know what exactly Vmax is. And the same thing for the Km. Well, the Km is half the Vmax. So if we're guessing what the heck the Vmax is, then how the heck can we know what the Km is? It's just an estimate. We estimated what Vmax was, and Km is 1/2 of Vmax, so we have to estimate what Km is. And that's a lot of estimations, okay? We have a lot of uncertainty there. So what people do is they take the reciprocal of both, they generate a line here, and then they're able to get an exact number, an exact measurement for Vmax and Km, an exact thing. And that's what they do and that's what they do here. They did an experiment, they took the inverse, and that's exactly how line work beaver plots work. That's the reason why. So that's D. And there's the explanation. See, I'm very confident when I answer this stuff. I know for a fact it's going to be the answer, and I click it. Confidence is key. I told you guys, for this MCAT, they want you to overthink. Don't overthink. You got it. If enzyme total was the concentration of lactase in the kinetics trial, okay, what expression gives the concentration of lactase in the commercial preparation of this enzyme? It's a little weird wording. What expression gives the concentration of lactase in the commercial preparation of this enzyme? Why are they wording it like that? Okay, they want to know. We have to know these are the dilution factors. First, we have to know what the dilution factor is. They want to know what the enzyme concentration is, what lactase concentration is, as an expression, okay, with the enzyme total concentration times the dilution factor. Okay, that's very tricky wording here. All right, if you guys got this one wrong, then it's okay. Like that's such tricky wording. Like the MCAT's trying to trick you here. Silly rabbit, tricks are for kids. They're trying to trick you here. So this is what, all right, we gotta look at the dilution factor. Okay, a stock solution of the enzyme was prepared by diluting 0.100 milliliters of the commercial preparation to 25 milliliters in the buffer solution. They want to know the beginning. They want to know the initial. Okay. So they want to know, what the heck do we have to multiply the enzyme total concentration times what? What do we got to multiply that by to give us the concentration of lactase in the preparation? Okay. So what do we got here? We went from 0.100 milliliters of the commercial preparation to 25 milliliters in the buffer solution. Okay, so that was a dilution there. So what was the dilution factor coming into this? This is a big dilution here. 0.100 milliliters, that's tiny. And then we went from 25 milliliters. I mean, that's still small, but 0.100 is very small. And we went from 25 milliliters. That's a big dilution. So in order to get the dilution factor here, to see what we diluted it by, it's you have to do 0.100 milliliters divided by 25 milliliters, and that's going to give you your dilution factor. So that dilution factor is 1/250. And then what they did here is the experiment. So is it just is 250 here? No, there's no 250 here. Experiments were initiated by mixing 1 milliliter of each substrate solution with 1 milliliter of the enzyme solution. Oh, okay. You have to take your 250 and multiply it by 2. Why do you have to multiply it by 2? Well, it's another dilution here. They didn't specifically say, oh, dilution by another 1 milliliter of enzyme solution. Like, they didn't tell us directly that it was a dilution here. But you kind of have to make a guess here that you have to multiply 2 by your 250 to get 500. That is a tricky question. That's a tricky question. That's a hard question. Yeah, that's the only way. I mean, you could kind of like take out stuff here, like 25. Like, no. 0.100 divided by 220, that's such a low dilution factor. That's definitely not it. 50, This no. This is no. 200 or 500, that could make sense. The dilution factor by 250, that is a little more obvious. But the dilution factor by, by times 2, how you have to take 250 multiplied by 2, that's complicated. That's not that visible. But yeah, you would have to multiply it by 2 because we're taking 1 milliliter of each substrate solution with 1 milliliter of the enzyme solution. So answer is 500. Pretty sure. Let's see. Boom. All right, let's go. Next question. Oh, that's it. All right, and that's it. So you guys, as you can see, this can be a little complicated. But the questions, the way they worded the other one was a little ridiculous. But if you can get these questions and you can break them down and they make sense to you, it's not, they're trying to trick you. A lot of times they're trying to trick you, honestly. Like, they don't have to word it like, what's this one? Like, you did not have to word it like that. You did not have to word the question like that. And you definitely did not have to word this like that. Like, you're trying to make us like find like a little needle in a haystack here. Like, this was a tricky one. But even if it's tricky, you can see, guys, by breaking it down, knowing what you know, knowing what you don't know, having confidence in your answer, realizing and looking like, yo, AAMC MCAT makers, why you gotta be like this? Like, why do you have to word it like that? That's so annoying. Like, say it out loud. Be like, yo, you're annoying for wording it like that. Like, here, G1, like, that could be a glycine 1. Like, why can't you just put GLU1 here? Like, that's a little, like, come on. But yeah, the more you guys do this passages, the more you guys go through it, the more you'll realize and be like, really, MCAT, like, really? Like, I see what you're trying to do here. And you become familiar, you get in the test maker's head, and you kind of realize like what the heck they're going to ask. And when you do that, that comes with enough practice, and then these passages become like a piece of cake for you. So let me know what you guys think in the comments of this passage. I really enjoy making these, guys. It's tons of fun. Yeah, subscribe because we're about to hit 100 subscribers, and I'll see you guys in the next video. Peace.